Okay, we're going to do the homework assignment here. And the first part of the homework assignment is to determine what's the smallest amplitude pulse of 1/10 millisecond duration applied at 1 millisecond after the start of a simulation will trigger a spike. Okay, so what I'm going to do is I'm going to use Python to execute this file called example.py. Let's see what example.py has in it. And so it has several statements of interest. The first one, of course, is the one that imports the H and GUI parts of the neuron module into Python. The second statement loads the cell class definition that we created earlier using the cell builder. And this is in Hoke, this definition, and it creates a class called the B-cell class. The third statement creates an instance of the B-cell class, and we can use the Python alias testcell to refer to this instance. The next statement reads the user interface that we set up earlier for working with this model to run simulations. So without further ado, -i example.py. And here we have our user interface, and we have our cell. Let's look at the parameters. Delay is 1 millisecond. Duration is 1/10 of a millisecond. Already has an amplitude of 5 nanoamps in there, but just let's start out with, say, a value of 1 for the sake of this exercise. Let's run a simulation. A little depolarization, but no spike. Let's multiply this by 10. And we get a big EPSB and a spike. Well, no, it's not an EPSB, I'm sorry. It's a big injected current, followed immediately by a spike. Okay, so we're above firing threshold. So halfway between 1 and 10 is what, about 5.5? Let's make this about, say, 5.5. Didn't run. It's still above threshold. Halfway between 1 and 5.5 is approximately, say, 4. Run a simulation there. Whoops. Low firing threshold. So halfway between 4 and 5.5 is about 4.8. Still below firing threshold. Halfway between 4.8 and 5.5 is about 5.1. Above spike threshold. Okay, so halfway between 4.8 and 5.1 is about 4.9. Okay, that's below spike threshold. Halfway between 4.9 and 5.1 is 5. So 5.0 is the spike threshold. 4.9 is not big enough to give us a spike. So it's going to be 5.0, 5 nanoamps. Okay, so that's the two significant figures. Okay, now one thing we should do before we move on to the next part of this exercise is to take a closer look at the initiation of this spike. If I click on Movie Run and I watch that red trace on the left of the origin, that's this part over here, negative distances, that's the membrane potential along the axon. Let me initialize this again, and let's make this run a little slower. And run. See how, even though the somatic membrane potential rises first, because that's where we're dumping the charge from the synapse, The spike doesn't actually initiate at the soma. The spike starts off to the left of the soma. Okay. Let's stop this. Initialize again. Let's change this to 15 milliseconds for the runtime. T-stop will be 15. Okay, let's do that again. So let's watch very closely this region in here. Init and run. You see what starts to come up to drag the rest of the cell along is the membrane potential at some little distance away from the soma. Okay. So the spike is actually initiating right around in here. See how that comes up? Somewhere around maybe 60 or 70 microns away from the cell body. Okay? And that happens in real cells as well, where the spike initiation zone is in the axon hillock initial segment part of the axon, and that's partly because the charge entering, the depolarizing charge entering the cell through the sodium channels, a lot of that gets sucked out of the axon and soma and into the proximal ends of the dendrites, so that the soma's charging is retarded, and you have to get a little bit away from the soma to get to a part of the axon where charge is building up quickly enough to depolarize the cell to trigger a spike. Okay, and the larger amplitude stimulus you apply, the closer that region where the spike triggers is going to be to the soma, and the smaller, the further away it'll be. Okay? All right. Now the next exercise is to replace the current clamp with an alpha synapse with a time constant of 1 millisecond, and then find what is the smallest maximum conductance that elicits a spike. So let's change this to an alpha synapse. Onset of 1 millisecond, tau is 1 millisecond, and what this is going to be is an alpha synapse. At the time of onset, its conductance starts to increase, and it reaches its maximum tau milliseconds after its onset. So this will start at t equals 1 millisecond, reach maximum conductance at t equals 2 milliseconds, and then gradually decay away. Okay, so if we just run a simulation, nothing happens because Gmax is 0. We don't know how big Gmax should be. Let's try 1. See what we get. We get a huge spike and a huge EPSP. We can't distinguish the two of them. I want to separate them from each other a bit. So to do that, let's reduce the stimulus intensity, cut the Gmax by a factor of 10. We get a somewhat more normal looking spike, but we still can't discern the EPSP separately from the spike. Let's divide this by 10 again. So now we have only 1/100th microsiemens as our peak synaptic conductance. Another simulation. We're starting to see what looks like the rising phase of an EPSP, on top of which a spike is triggered. Let's cut that again. Too low. So the actual spike threshold, the peak conductance that's just big enough to trigger a spike, is somewhere between 0.001 and 0.01. So let's try 0.005. Init and run. Not big enough. Try 0.007. Init and run. Good, we got a spike. So between 0.005 and 0.007, let's try halfway between. 0.006, getting a spike. So that's still a little bit too large. Let's try 0.055. Too small. Try 0.057. Just big enough to get a spike, and 0056, too small. So the threshold synaptic conductance to trigger a spike is 0.0057 microsiemens or 5.7 nanosiemens. And we're getting this strange looking separation between the EPSP and the spike. Let's let that run for a full 25 milliseconds. So what's going on in here? Why is there this separation? Why isn't the spike arising from the EPSP? Well, let's take a look at what's actually going on in the cell. Let's click on init and run and let things evolve. Let's see what happens to membrane potential. So our EPSP starts. And then, the spike actually triggers somewhere out here 200 microns from the cell body and then spreads back into the cell body. That's what's going on. Okay, so that's why we're seeing this strange looking separation between the EPSP and the spike. The EPSP isn't strong enough to trigger a spike closer to the cell body, but the depolarizing current that it injects into the cell can spread far enough into the axon to start opening sodium channels out here. And those sodium channels start to regeneratively open, and we see a little bump starting up, and then the full-blown spike emerges at 200 microns from the cell body, and then spreads back and out into the axon as well. Okay. So let's stop and let's see what happens if we increased Gmax to say 0.0058. What is going to happen? If I'm right, the spike trigger zone should move closer to the cell body. Let's do an init and run. Okay. And the spike is now triggering at about there, a little bit shy of 100 microns from the cell body. Okay. Let's stop and let's take a look at that again. Init and run. And see how that little bump arises and the spike trigger zone is somewhere around 100 microns from the cell body. Okay, so increasing the size of the synaptic input moves the spike trigger zone toward the cell body. Okay.